Hello and welcome to Engineering Dynamics. I'm your host, Dr. Walk, and today we're going to be going over an example. I have tried to record this video 3 times now. So there's a hurricane outside. The dogs are going crazy. There's no daycare, so the kids are out there. So I moved into this little closet area and I am hoping that this works. Okay, so fingers crossed this is the last recording and I can get it out to you guys. The question asks, a vertical disc of radius r, little r, is attached to a horizontal shaft of length big R as shown. The shaft is rotating at a time-varying rate phi dot, while the disc is rotating at a time-varying rate theta dot. There is a fixed point P on the rim of the disc, while a missile is flying overhead at a fixed height with a trajectory as given. In this example, we want to find the inertial velocity of point P. You could also finish the example finding the acceleration and the velocity and acceleration of point P as seen by the missile. But what we're going to do is just try to focus on finding the inertial velocity. I'm going to show you 2 ways to find that, and you can see which one's easier and why we would do it one way versus another. Okay, so before we get started, let's go ahead and try to just figure out, I'm going to move me up here. Why don't we just try to figure out what this thing is even doing? And then we'll go back and try to figure out what we're trying to look for, what we're trying to find. So right now we have 2 reference frames. We have a reference frame here, which is our N reference frame. And here we have our E theta ER reference frame. In my last video, we talked about 3 different reference frames: the Cartesian reference frame, which was inertial, and then we talked about polar and normal and tangential. These ones are not X, Y, and Z, or I hat, J hat, and Z, K hat. They're labeled something else. And you're going to find that in industry and in your careers and even in different textbooks. Everyone uses different types of notation, but just by definition, you can figure out what type of frame is it and what type of motion is it describing. So let's go ahead and go through that. Here we have N1, N2, and N3, and it is saying that this pole here, which runs through the origin, let's go ahead and label that. So we have our N frame and our N origin, and N is spinning at a rate of theta dot, or excuse me, phi dot. N is rotating, so N is rotating at a rate of phi dot. And R, the shaft R, is attached. Okay, it's rigidly attached to this frame. So as the pole rotates, the shaft also rotates at a rate of phi dot. So big R also rotates at a rate of phi dot. Then this R, it's kind of hard to see this, but this shaft actually goes all the way to the origin of our next reference frame. Okay, and the origin of our next reference frame, we are going to label that E. That's our E reference frame. So we have an N reference frame and we have an E reference frame. This is interesting because our E reference frame is also going to rotate in the horizontal at a rate of phi dot, but it is going to rotate in the horizontal at a rate of theta dot, in the vertical, excuse me. It is going to rotate in the vertical at a rate of theta dot. Okay, so, and big R was related to phi dot. Little r is going to be related to theta. And the reason I'm going to say that is because I'm going to draw a vector here that is going to attach the origin to P. And we're going to call this little r. That's a vector, little r. And the vector, little r, is pointing to the point P, and it is being viewed from the reference frame E, from the E reference frame. And if we go back, we can also define this vector a little bit more. So we called this vector big R, and big R is pointing to the origin of our E reference frame. So it's pointing towards E, and it's being viewed from N. It's It's being viewed from n. And now we have to ask ourselves, okay, we understand the problem. What are we being asked to find? We're being asked to find the velocity. We're being asked to find the velocity of point P, velocity is a vector, as seen by the inertial frame. So find the inertial velocity and acceleration of point P. So if it's being seen by the inertial frame, this is what we're trying to find, okay? So we have to draw and what is the kinematic relationship for velocity and position? Well, velocity is simply the derivative of position in terms of time. And I know position is usually written as r or maybe s. What we're going to do is we're going to define a vector. So let me back up. So this is talking about a position vector. We have to take a derivative of a position vector. Well, we have to define what that vector looks like. So if we're taking its derivative, we have to come up with a vector, let's just call it Q for right now, that points to the particle P, and that's being viewed from n. So I can take this and I can say, well, the velocity of my vector Q P pointing to P in the n frame is going to equal the derivative of its position. Okay, I hope that kind of makes sense here. So this is our kinematic relationship, but I don't want to use, so this would be P and N. I'm hesitant to use R to represent our vector that we're going to make because we have a little r already and a big R already. So I think we should just pick another letter, okay? But understand that no matter what you pick, it's still going to be the same thing. It's just going to be a position vector that locates the point P. It's a position vector that locates the point P being viewed from the n frame, okay? So we can say that that's Q. So this right here, this is going to be the position vector locating point P viewed from the n frame. All right, so now let's use relative position to get what does our position vector look like. Actually, let's just keep that there for a second. So what does our position vector look like? Can someone tell me what is our position vector? Well, our position vector is going to equal the sum of these two vectors. So let's draw this out. If I have a point here, and this is my fixed reference frame, but I have a moving point here, and I have a moving reference frame here, and I have a point here. Well, this point can be viewed from my fixed reference frame, but it also can be viewed from my rotating reference frame, and my fixed reference frame can also view the rotating reference frame. So we're just going to kind of rename, just put the names on here so we know where we're at. So this is little r. Little r points to P from E. And remember that this is P. And remember that this little guy is E. This little guy is N. And then we have our large pink vector. And the pink vector is going to be the one we just made, that we drew, right? Wasn't given to us, is going to be QPN. So this is really just relative position. And this states that the long vector here is going to be this vector plus this vector. So this is going to equal, if we move it down here, is going to equal REN plus RPE. I'm going to do like a couple of side little mini lectures. I might as well. You guys can skip through it if you already know it. So here we have some students question, how do you know that you have to add these two or subtract these two? And because sometimes vectors will be in the same direction, sometimes they'll be in opposite direction, sometimes they'll be mixed into a mechanism that's just really hard to understand and to figure out. So there is always a way, a foolproof way of finding out if you subtract the two vectors to get the third or if you add them to get the third. And that way is using closed loop. A closed loop is just saying that this mechanism doesn't have an opening, right? All of the vectors connect to each other, whether they connect through their tails or their heads, they're connected. So it tells me that all three of these have to equal 0, okay? So it's called loop theory because you go around in a loop. You can start anywhere you want as long as you end at that same position. So I can go around the loop this way, or I can go around the loop this way. It doesn't matter which way you go. Okay, so let's randomly go from here up. So we're going to have, if I start from the tail of the vector and I work my way to the head, that means that it's positive. So it's going to be NRE. I continue my loop and I see that this is going to be another tail to head. So that's another positive. So I'm going to do positive little r. And then all of a sudden I got the head of the vector. So that means that now I'm going negative because I'm going from head to tail. So this one is going to be minus QPN, and I'm back to the starting point. And again, this is a closed loop, so it has to equal 0. So look at that. If I move Q over, I get that equation. Now, for those of you who don't believe me, why don't we just quickly go around the other way? So if I go from tail to head, I have QP. Then I go around, I hit the head of the next vector, that's negative RP. Oh, I hit another head, so that's going to be negative RE equals 0. And look at that. If I take these two to the other side, I once again get my position vector. So if our instruction is asking us to find the velocity of the point P viewed from the inertial reference frame, so we can actually move on from here and just take its derivative. But if the instructions asked you to find the position vector viewed in the inertial reference frame, and that was the final thing it wanted, you cannot represent a vector using different unit vectors. What do I mean by that? I sound like I'm talking gibberish, but hang with me. If I write these out, this is going to be expressed in the normal frame. That means it's going to have unit vectors n1, n2, and n3 in it. This is represented in the E frame, which means this position vector will be defined using ER, E phi, and E3. That is not okay. So if this was the final answer, this works in terms of, because your E's cancel here and you have an N and a P left, so you have N and P. This works great if you're just using relative velocity. It gets hairy if it's asked for the velocity in a certain reference frame. So now you have to make sure all of these are the same. So that means that I would have to stop and I would have to represent my final position vector in the same reference frame. Okay, so I want to move on to velocity using this one and this one. So I'm going to break this up into two parts. We're going to first solve it using this way, because my instructions don't say anything about giving them a position vector in the inertial reference frame, it just wants velocity. So I can change this very last term at the last second and then represent the velocity in the normal reference frame. Then I'm going to go back and I'm going to show you that it's a lot faster, I think, to do it this way. However, you get more practice doing derivatives of unit vectors in this way. So that's why I want to take the time to show it that you can do it this way, just for more practice and understanding the vectors. And if you watched my previous video, you'll see that I'm using the same techniques, okay? So let's go ahead and say, let's first write, what does big R, what is RE? And let's go ahead and represent it in both the E frame and the N frame, and let's just see what we get. So if I look at this R vector here, okay, this R vector is in line parallel. It's on the same line as ER. So ER here, you have ER here, and the dot is just on this axis. So that means that its position is simply some magnitude R on the axes ER. Okay, that wasn't, that was very easy, which is why, sometimes it's just easier to represent them in other frames, because now look how long it's going to get if I say, well, what is R in terms of the normal and the inertial reference frame? So now I have to say, well, how do I translate ER onto the inertial reference frame? How would I do that? Well, I'm going to take both frames. I'm going to start with my frame 1. This frame here, I can see that the unit vectors in the horizontal plane is marked by N1 and N2. So I'm going to start with N1 and N2. This is my horizontal plane. And between N1 and N2 is the unit vector or the axis ER. That's ER. So we have ER here. And so E phi is perpendicular to that. And N1 and ER are rotated by an angle phi. They're separated by some angle phi. Using trigonometry, we also know that that's phi because N1 and N2 are perpendicular to each other, and so is ER and E phi. So now I can project my ER on to my N frame. So if I break this ER up into components, I have that it's going to be cosine phi N1 plus sine phi N2. So all I have to do is put this in here. So I know that it's going to be some magnitude. This is going to be cosine phi N1 plus sine phi N2. And now I have this term. So now I need this term here. How do I get that term? So now I'm looking for the position vector of P, and we want it in the E frame. So if I go to my picture here, I'm going to see that little r, so I'm looking for RP in the E frame. So I'm in the E frame here, okay, and it's at my vector, this blue vector, okay, and I can see that if I project this down to my my coordinate system, so maybe it's not as easy to see as I'm thinking. So if you have the disk, the unit vectors that align with the disk, because it's in the vertical plane, are going to align with E phi and E3. And the point is somewhere, it lies somewhere here. And this is R, and they're saying that the angle right there is theta. So all I have to do is project this onto here and this onto here. So you're breaking it up into components. So I'm going to have R, some magnitude R, sine theta E phi, plus R cosine theta E3. So this is going to be, we're going to take this, by the time I scroll down, I'm going to forget what I wrote. So I'm just going to copy that, and I'm going to push it down here. Oh, it took everything. Oh my. Oh my. Okay, that didn't do what I wanted. So I'm going to do RP was R, little r, sine theta in the E phi direction, plus R cosine theta in the E3 direction. And that is going to be my, this one here. So now I have two things. So let's go ahead and put those all together. I'm going to have that my position of point P in terms, actually I'm just going to do it here for now because it's not really in terms of anything. So like up here, I think it would be proper if you just didn't put a frame for now. I don't know, maybe, I don't know. I don't know if it matters. I just don't want to confuse anyone. Okay, so let's just do the position of P. So the position of P, we said was big R, which is this one here. So it's going to be R cosine phi N1 plus sine phi N2. and we're going to add that to, and we're doing the first one, so we're going to leave it in the E frame, and that's going to be r, little r is a constant, sine E phi plus r cosine theta E3. Okay, so now we have the position and we want the velocity. So we have to take its time derivative to get velocity. So let's go ahead and do that. Let's go ahead and say, well, what is the velocity of point P? The velocity of point P, the magnitude of r isn't going to change. N1 and N2 are constant because those are the unit vectors that are used in our inertial reference frame. And remember, our inertial reference frame, the unit vectors are not going to change in direction, and unit vector has a magnitude of 1. That's not going to change. So if we took its derivative, it would be 0. So really, when we take this derivative, we're just taking the derivative in terms of time for these parameters, not the N1 and N2. Note that's not going to be the case over here. So we have to use U substitution. So we're going to say that this is going to be phi dot negative sine phi n1 plus phi dot cosine phi n2 plus, here we are saying that r is a constant, so that can stay outside the loop. That's fine. But here, this is going to be a variable, this is a variable, and we take the derivative of this. So we're going to have to use U sub and the product rule. So I'm going to say the derivative of the first, which is going to be theta dot cosine theta E phi plus the first times derivative of the second, which is going to be sine theta, derivative of the unit vector E phi in terms of time, plus, and now I'm going to here, oh, I factored in the r. Sorry, that r shouldn't be there because I factored it out. Sorry about that. Here we're going to say, well, E3, is that a variable or a constant? Yes, it's on the rotating frame, but E3 actually stays up the whole time. So because this thing is rotating around, so N3 and E3 are going to stay vertical the entire time. Okay, the disk is going to spin about ER, but it's given an angle. So they're saying that E3 is going to stay up. Okay, they're saying that E is going to stay up. So that means that really we just are going to say that the derivative of cosine theta is going to be negative theta dot sine theta E3. So I'm left with what is the derivative of a unit vector? I have no idea. I have no idea what the unit vector of E phi is, but I do know a way to find it. And how we find it is we're going to use this concept here. So I'm going to take this, hopefully that works this time. I'm going to take this and I'm going to put it down here. And I'm going to say, okay, I have an expression for ER, but I'm looking for the derivative of E theta ET. So I'm going to take I want to take an expression of, well, what does E theta equal in the N frame? And that is going to equal negative sine phi N1 plus cosine phi N2. But I'm asked for the derivative, so let's go ahead and take its derivative. So we're going to take the derivative of the unit vector E phi in the N frame with respect to time. And this is going to equal negative phi dot cosine phi N1 minus phi dot sine phi N2. And then I'm going to say, okay, well, let's factor out a negative theta dot. Oh, it's going to be his nap time soon. Sorry, hang on. Okay. I'm going to also see if I can move myself down here. All right, let me get out of the picture. Okay, so here we're going to factor out that phi dot, and I'm going to say, okay, cosine phi N1 minus, oh, but I factored out the negative, so it's a plus, sine phi N2. And here, check this out. This is the same thing as that. So I can say that oopsies. So I can say that the derivative, this guy here, is really equal to negative phi dot ER. Okay? So I'm going to then, let's go ahead and clean this up because I think that was the only unit vector I needed. So let's go ahead and rewrite this down here. Let's go ahead and bring the QP down. So we can do, let's write the velocity of point P is equal to R negative phi dot sine phi in the n1 direction plus phi dot cosine phi and in the n2 direction plus R theta dot cosine theta in the E phi direction plus sine theta phi dot in the E to R direction. We're going to have to make that negative like that. And then our last term, oops. Does our last term have an R in it? It does. So we're going to have to get there to that. And then we are going to do minus theta dot sine theta E in the E direction. All right. So this is not what they asked for though. This velocity vector, and this is a velocity vector, it's got to have that dot, it's a time derivative. So we have to say, all right, well, this isn't what they asked for. They asked for what is the velocity of P in terms of the normal frame. So to get that, the first parameter, that's great. This is N1 and N2. You're fine. You can bring that right down and that can be part of your answer. We're good there. N1 plus phi dot cosine phi N2. That's great. This is the part that is concerning. We can't say that this is in the normal frame because this is in our rotating frame. So that's not legal. We have to project these guys. Now, the first one, this E3, that's pretty easy. E3 is simply N3 because, again, remember that they stay parallel to each other. So we can just make this one an N3 and call it a day. These you can't. You will have to represent them in a different frame. So good thing we already did though. So this E theta really equals this part here. And ER is equal to this part here. So all we have to do is plug these in. So let's go ahead and do that. This is going to be plus R theta dot cosine theta E theta, which is going to be our negative sine theta N1 plus cosine phi, N2, minus sine theta phi dot, and then we have our R, our ER, which is going to be cosine phi N1 plus cosine phi N2, and then that last term, which is going to be negative theta dot sine theta N3, let's rewrite that, N3. So this is N3. N3. All right, let's clean this up because this is a lot. Now I can officially write that this is the velocity vector of P viewed from the N frame. And this is going to equal, let's group our N terms. So we have an N here, we have an N here, and an N1 here. So we have negative R phi dot sine phi minus R theta dot cosine theta sine phi minus sine theta phi dot cosine phi. All of that is in my N1 direction. Now let's do the same thing for N2. We will have plus R theta dot cosine theta plus R theta dot cosine theta plus times cosine phi. And then we have another n. We have a minus sine, we're going to have a phi dot, sine theta, sine phi, and that's in the n2 direction. And then we have our last term here, which is going to be negative theta dot sine theta n3. And that r, we forgot to sub it in. So this r has to be put into this term. And this one, this r subs into all of this. Tricky little r. So I'm going to go in and just kind of fill these in. This has an r, and so does this one. Sorry about that, guys. So this has an oops. So this has a phi dot and an r. And there's one more r in here. That pesky little r. I think that's the hardest part of these problems, is just bookkeeping. Okay, all of those have little r's. So these two terms have a little r, and these two terms have a little r, and then our final term will have a little r. Okay, so that is your answer, and that is doing it the first way. That's doing it if you really wanted to practice taking derivatives of unit vectors. So we just did it this way. We could have also done it this way. So if we take this guy, I wonder if it would just be better if we just started all over. Okay, so let's do it one more time, but this time we're just going to do it straight from how we would represent it. This, I still think if I was a student setting up this problem, I still think I would use the relative velocity to make sure it worked out with the signs. And then I would say, okay, now I have to put it all in the same frame. So I think I still would go through the loop part and make sure that mathematically it was correct. And then I would say, okay, I have to take this and project it onto there. So if you've done all that, now we can move forward with this one. If we look at if we look at big R, in the n frame, I can see that it is going to have a component in n1 and n2. So this just looks like, this is n2, this is n1, my r comes out somewhere here, and this is phi. So I'm going to say that my REN is going to equal some magnitude of R cosine phi n1. Oh, and excuse me, this is a big R. This is big R. So this also has to be big R, because some magnitude. And then it's going to be plus big R sine phi in the n2 direction. Okay, and that gives us this one. Now we have to do NRP. So the position vector R. So that's this one up here, and we want to relate it to this one. This one might be a little bit more tricky. So let's take a look at this. If we want to represent, we say, let's move it down here a little bit, and we have that it's going to be in E3. So this is going to be E phi and E3. And and this is going to be P. This is going to be theta. So I think I would still represent little e in E first, just because it's not as easy to view. Because right, that's in the vertical plane. So if I moved this over, it would be between N3 and N2. And yeah, that one's a little harder for me to see. So I think I'm going to just represent it here, and I'm going to have that this is little r. So this is going to be r sine theta in the E phi direction, and then it's going to be plus r cosine theta E3. Now this one's easy because that's just N3, but this one here, I am going to have to change that. So I can say that this is going to be, now it's going to be NRE equals r sine theta, I'm going to come back and represent that a different way, plus r cosine theta n3. So now I have to project this one, E phi. So E phi is going to lie in the between n2 and negative n1 axes. So I'm just going to draw this here because take it out of like the most difficult mechanism, right? And then you can project it a little bit easier. So this is going to be E phi and ER, and this is going to be, I'm sorry, wait, theta is coming off of E3, but we are looking at the horizontal here, so that's going to be phi. We're going to represent it with phi. And phi is between N1 and E. So let's go back, erase that little line. And we have that this one is phi, and this is phi. So I'm going to say that E theta is equal to negative sine phi N1 plus cosine phi N2. So that's going to go here. This is going to be negative sine phi N1 plus cosine phi N2. So my position, my position vector. So that is, why did I write an E here? Oh gosh, I'm getting tired. This is not an E. Why is that not an E? I feel like I have to do this over. I'm not going to do it over this a fourth time. So R, little r, is pointing to point P, and it's being viewed from E. So same down here, okay? All right. So now we are here. All right, so let's go. Let's put together what is our Q vector. What's our Q position vector of P in the normal frame? It is going to equal R cosine phi N1 plus big R sine phi N2 minus R sine theta sine phi N1 plus R sine theta cosine phi N2 plus R cosine N3. All right, so that's our position. Now all we have to do is take our velocity. So we have to take our time derivative. If we take a time derivative, we can represent that vector with a dot, and of course it's going to be in the inertial reference frame. So R is a constant, N1 is a constant. This is going to be negative, and remember you still have to use U substitution because it's still a time derivative. So we will have this one. That's done. Second term, again, big R is constant, N2 is constant. So we will have an R, we're going to have a phi dot cosine phi N2 minus, now we will have to use the product rule. So either way you do, you're going to have to use product rule. At least you don't have to take a derivative of a unit vector, but you will have to take a product rule. Interesting. This is the first time I'm doing it. So, okay, interesting. So let's say we have first, we're going to take the derivative of the first. So that's going to be theta dot R cosine theta sine phi N1 plus, then you have to do the second, which is actually still going to be a negative because we still have that negative out there. So the derivative of sine is still cosine, so that's going to just be a negative still, doesn't change. So first we're going to do minus R sine theta phi dot sine phi N1 plus, same thing here, we're going to do R theta dot sine theta cosine phi N2 plus the first times the derivative of the second, which is theta dot R sine theta sine phi, and it will be a negative. And that's in the N2 direction, minus, because that's going to be theta dot sine theta, there's an R and an N3. Oh my goodness. All right, so now let's say, okay, well that was it though. You didn't have to take any unit vector derivatives. So that's interesting. So now let's see if we can clean this up and see if we get the same answer. We better get the same answer. So we have negative phi dot r sine phi minus theta dot r cosine theta sine phi minus r sine theta phi dot sine. Okay, let me actually rewrite this term because they're all out of whack. So you want to get in the habit of like putting the highest rank first. So we're going to put, so we have this term is done, this term is done, we're working on this term. So let's take out that phi dot. And then r sine theta sine phi. All of that is in the n1 direction. Then we're going to work on the 2's. So we have a phi dot r cosine phi. And oh my goodness. Okay, that's the first n term, and then we have plus theta dot r sine theta cosine phi minus phi dot r sine theta sine phi. All of that is in the n2 direction. And then we have that last term, r theta dot sine theta n3. Okay, so we get the same answer as we did before. So that's that problem. I think there's only one more thing that we can kind of learn here, and I don't know if I want to do it here in another video. This here, this can be done using the cross product, using velocity, angular velocity, and position. Yeah, why don't we just go over a quick mini lecture? Okay, so let's just look at when we project a vector onto axes, really. That's all we're really doing. So let's take a look at two different ways of doing this vector transformation. So if we take our n1 and our n2 frame and we lie our ER and our E phi in that frame, and we know that they're rotated just by some phi, and then trig says that's over there. Now we can say this is still legal, right? ER is equal to, it's a unit vector, so magnitude is 1, cosine phi n1 plus sine phi n2, and its derivative der dt is equal to negative theta dot sine phi dot sine phi n1 plus phi dot sine phi n2, and we can do the same thing for E phi, and this is going to be negative sine phi n1 plus positive cosine phi n2, and its derivative in terms of time is going to equal negative phi dot cosine phi n1 minus phi dot sine phi n2. Now here's where I'm saying I want you to stick with me here. We know that the cross product takes two vectors and you cross those two vectors together and you get a third vector that is orthogonal to both of those vectors. So this is interesting. If we have a horizontal plane, ER and E phi, if we cross these two, we would get, so if we said ER cross E phi, we're going to get that third, which is E3. And the same with N1 cross N2, you get N3. Okay, so keep that in mind. Now I'm going to say if, let's do this. If I had, I'm just going to draw a little picture here and kind of show you where I'm coming from. If this is X and Y and you have some point here, P, and you draw a position vector to P, this is your position vector in your xy plane. Your velocity vector is always perpendicular to your position vector. So this is v. And we're going to learn more of this in rigid body dynamics, but I just want to like put it out here to introduce it to you. So I can say that v is equal to omega cross r. And I can say that because v and r lie in the horizontal plane, and omega is the third. That is because this is rotating about, so this point can go here. This is velocity, this is r, and it can just keep rotating around and around and around. And it's rotating about that axis, omega. So if I say, well, what is the derivative of er dt? That is equal to, well, it's going to be equal to r omega is going to be phi dot. So this is going to be phi dot in the E3 direction. And we are going to cross that with the third vector, which is going to be E phi. Because this is velocity, this is omega, and this is position. This should be, I'm sorry, ER. So now we have, this is velocity, this is your omega, and that is your position vector. So what is the derivative, what's the cross product of these two? The cross product of these two is going to be, this is a scalar, so that pulls out. What is the third unit? The third unit is E phi. So the derivative of the unit vector ER dt is equal to phi dot E phi. And if you come over here on this side, the derivative of ER dt is going to be negative theta dot. And then look at, if I factor out an theta dot, I left with a sine phi n1 plus a sine phi n, that should be cosine. I hope I didn't confuse you there. Oh man, I don't want to redo all this. Here. This here is a cosine. I think you guys knew that. That's a cosine. So this is a cosine. So here we can see that, here. So we can make the connection that this here is the same thing as, and we have our negative in there, is the same thing as this. So long-winded, dE dt is equal to theta dot, and then I'm going to switch this for this, which is E theta, or E phi, excuse me. Okay, we're done. I'll probably do another video of this explaining it in depth, but okay, I hope that helps you guys and it helps get us ready for your Tuesday exam.